So let us start with our invited sessions. So let me introduce our first speaker. So today's first speaker is Professor Yarema Okhrin. He's from Business and Economics Schools, University of Augsburg, Germany. And his research interests constitutes of quantitative methods in economics and finance, statistical process control, applied and financial econometrics, dependence modeling. He is currently editor-in-chief and advances statistical analysis and was vice president of the German Statistical Society, which many among his academic endeavor, other than even writing books also. So Professor, it's yours, sir.
Okay, thank you so much. For having me here. I'll present the paper on optimal shrinkage estimation of high-dimensional portfolios, and it is a joint paper with Taras Bodnar from the University of Stockholm and Nestor Paroda from the Technical University of Delft. As the title tells us, their whole paper or the whole presentation will split it, so to say, in three different components. First, we'll talk about optimal portfolios. So it is like a classical problem in asset allocation in finance. The second component is about shrinkage estimation. So they will suggest a new type, a more robust type of an estimator for the optimal portfolio weights. And the third one is about high-dimensional portfolios. So there are modern technological advances, they allow us to build portfolios not just from 10, 20, or 30 assets. We have access now nowadays to thousands of different assets. And the question is, do this amount or this large number of potential assets in our portfolio has some impact on the performance and on the performance and on the statistical estimation or on the statistical properties of their optimal portfolios? So I'll start first with some motivation why this high dimensionality is or can be dangerous for asset allocation, and then move slowly to their to the portfolios and to their shrinkage estimation. Yeah. So we know what is asymptotic. So in statistics, typically, if our sample size goes to infinity, we talk about the asymptotic behavior, asymptotic distribution, convergence, and so on and so forth. In most of those cases, our dimension is, however, fixed. So if we fix the number of the assets in our portfolio, say it is 10 or 20, then we don't have any problems. Everything will converge asymptotically to their population counterparts. And all the classical limit theorems, like central limit theorem, will be fulfilled. Now, the problem is that if we increase our portfolio, we will automatically let our dimension P in some sense go to infinity. But simultaneously, we need to increase our sample size N in order to estimate all the components, all the parameters we have in our asset allocation problem. So the large dimensional asymptotics we understand if, or we have the large dimensional asymptotics, if the ratio of P to N tends to a positive constant. It means that P goes to infinity, N goes to infinity, but their ratio of their dimension and the sample size goes to a positive constant C. This C can be, for example, smaller than 1, then our dimension is smaller than the sample size, but it can also be larger than 1. In that case, our dimension is larger than the sample size. And in that case, all the classical, or most of the classical limit theorems do not hold anymore, and we suffer from the so-called curse of dimensionality. Now, why it is relevant in finance? In finance, for example, if you have 1,000 assets and would like to build a portfolio of those assets, then we need at least 1,000 historical observations. But those 1,000 historical observations, they go over a very long period of time. For example, if we pick up monthly data, then with monthly data, we'll have to go over like 100 months. And in most of the cases, it is too long. We take too old data to build our portfolio. So we try to shorten our historical data, to shorten the sample size, and then our dimension becomes comparable or even larger than their sample size at hand. Now, why all those things are problematic? Let's have a look at a very simple example. Assume that we are interested in our covariance matrix, sample covariance matrix Sn, and the true covariance matrix is the identity matrix. So we have a diagonal matrix with ones on their diagonal, and else we have zeros. If you look at the log of the determinant, so in fact here it is log of the determinant of the correlation matrix, Then it is obviously the sum of the eigenvalues. And this quantity is extremely popular in statistical theory. You can use it, for example, to quantify their entropy of a system. You can use it to quantify some kind of dependencies. You can use it for testing and so on and so forth. So the statistics here, Tn, is extremely popular in multivariate analysis. Now, what happens if you let p go to infinity, if you let n go to infinity, but fix our dimension? In that case, our sample covariance matrix will converge to their identity matrix. This implies that all eigenvalues will converge to their true counterparts to ones, log is equal to 0, and the whole quantity will converge to 0. So that's what we have down here. Our Tn converges almost surely to 0 if n goes to infinity. For testing purposes, we have this normalization here. So if you multiply Tn with square root of n over p, it will get something what is asymptotically normal with 0 mean and variance 2. So this can be used for all possible purposes. But this holds only if our p over here is fixed. Now, if p goes to an infinity too, so p goes to infinity and n goes to infinity, but their ratio converges to some c between 0 and 1, so we consider this one case here, then 1 over Tn converges to some function of c, and this function here can be determined explicitly. It's over here, and it is negative. So it is not 0 anymore, it is some negative constant. Second, the asymptotic distribution. So if you use the same normalization as up here, if you take this normalization and apply it over here, then we see that this quantity here diverges to minus infinity. So it is not only non-normally distributed, but it also goes simply to minus infinity, just because our dimension goes to infinity almost with the same speed, or with the same speed as their sample size. Now, why this happens? To see that, just very basic mathematics here. So consider that, assume that we have two vectors here. The true vector is s, and the estimated vector is s hat. And we consider the simple Euclidean distance between those two vectors. So we have the sum, I goes from 1 to p, the difference between the estimated quantity and the true quantity. And now we let for this sum n go to infinity, once with fixed p and once with infinite p. So if p is fixed, then we have a finite sum over here. Every single element is consistent estimate of Si, so every single difference here converges to 0, and the whole total sum converges in probability to 0 as well. So that's pretty straightforward. If we let p go to infinity, then the number of the summons in this sum here goes to infinity as well. So, and it is not clear if this sum over here is going to be dominant. And as a result, we don't even know where the sum will converge to if both n and p goes to infinity. So we have over here, both p and n go to infinity, the number of summons go to infinity, and the limit is simply unknown. So that's what, there's a simple reasoning that the asymptotics, if the dimension goes to an infinity, is not straightforward and needs a very thorough discussion. So this was the motivation for this high dimensional problem, and now we come to their optimal portfolios. So we consider here a very classical setting. We take expected quadratic utility. So this is the expected return of the portfolio and the variance of their portfolio. The parameter gamma here is the risk aversion coefficient, and we would like to maximize this stuff here. We assume that the sum of the weights is equal to 1. This is with their constraint over here. And we allow for short selling. So we assume that W's can be positive or negative. It is a very simple quadratic optimization problem. And we can show that the optimal portfolio weights are given by this quantity here. So in fact, we have some sigma minus 1. We have some like linear forms in the inverse covariance matrix, and we have quadratic forms over here, and we have some more complex structures over there. Now, all those portfolios will lie on the efficient frontier. All of you have seen this kind of a hyperbola there, and every single portfolio on their efficient frontier will be characterized by their risk aversion coefficient gamma. Now, of course, this works only in theory. In practice, we will need some more stuff. So first, we need the expected return for the portfolio. What do we expect from our asset allocation strategy, and the variance, or like the risk measure. And then this efficient frontier that I mentioned on the previous slide, it is a hyperbola characterized by the following equation. So R and V are the running parameters. On the horizontal axis is V, on the vertical axis is R. And then RGMV and VGMV are the expected return and the variance of the global mean variance portfolio. It means if the risk aversion coefficient goes to infinity. And S, it is a very important parameter. It is the slope coefficient of the efficient frontier. So if S is very small, then their efficient frontier is very flat. If S is very large, then our efficient frontier goes quickly up or increases very quickly. So in fact, all those quantities on this slide and on the previous slide, they depend only on mu and sigma. So with mu and sigma, you can get any characteristics, any characteristic of our portfolio and any characteristic of our efficient frontier. Now, mu and sigma are unknown, of course, and in practice, they must be estimated. And typically, this is done just by the mean for mu and by the sample covariance metrics for the matrix sigma. So what we do afterwards, we just plug in those quantities here, y bar and S, into the formula for the optimal portfolio weights, and those are their like feasible, in practice applicable asset allocation strategy. Now, everyone knows that if we simply apply these formulas in practice, then the performance is going to be very poor. So it is well documented in the literature that despite of all the nice theoretical advantages, the practical aspects of their classical portfolio theory are pretty poor, and this is because of several reasons. First, we have plenty of estimation risks. So what we have here, this estimation of mu and estimation of sigma, it feeds a lot of uncertainty into our portfolios. Second, we also have some model uncertainty because we assume that we have a quadratic utility function. No one can be sure that his utility function is really a quadratic one. Maybe the distribution is also important. If the asset returns are not normal, this also induces some kind of uncertainty in there. And finally, due to hardly predictable components. What do we mean by that? Because we estimate our parameters using historical data, and there is no certainty that the same parameters will also persist into the future. So those three components here, they actually tells us that everything what we do is extremely uncertain, and they explain their poor performance of their sample portfolios. Now, let's come back to our high-dimensional problem. So here I show 4 different efficient frontiers. The first one, the black one is always the true one, and the red one is always the sample one. So we estimate the parameters and plot the corresponding efficient frontier. Now we have 4 pictures, and on the first one we have P equal to 10. We have 10 assets, 500 observations. It means that our C is 0.2, 0.02. Here P is 50, 500, our C is 0.1, here C is 0.5, and here C is 0.8. So it means that we increase our ratio between the dimension and the sample size. And what we observe, if our ratio C is relatively small, then our sample efficient frontier is fit pretty nice. So it is pretty close to the true efficient frontier. If we increase our C, so if we increase the dimension but keep the sample size constant at 500, we see that the difference between their estimated efficient frontier and their true efficient frontier, the black curve, increases dramatically. And this has a very negative consequences on our asset allocation problem. Because if our efficient frontier is very high, then it means that we expect a very high return from our portfolios for the same level of risk. And this implies that we get very super optimistic. So we believe in this expected return and get at the very end very disappointed if we observe that the true return is much lower than what we have expected on this red line. So this implies that in the high dimensional case, if we have a very large portfolio, our efficient frontier is too optimistic. It overestimates heavily the expected return on their underlying portfolio. And this is due to this divergence problem I have shown a couple of slides before. Now, where this comes from, this actually comes from these covariance metrics that we have there. So if you recall the formula, we see that all those quantities, they depend on the inverse covariance metrics, on the so-called precision metrics. And in fact, it can be shown, that since the classical theorems do not hold anymore, then the expectation of our inverse covariance matrix is some constant eta times sigma to the power -1. And this eta here is some function of n and p. And just very simple example, if our dimension is half of the sample size, So we have 100 days of daily data and 50 assets. Then in that case, our eta is going to be 2. So we have a bias, a multiplicative bias of 2 for our inverse covariance matrix. And it means everything what was in the formulas before there shall be multiplied with 2. So in fact, it is very heavy bias. So this is again formalization. What happens over there? If we try to compute like the expectation of the precision metrics for large values of p relative to n. Now, to solve the problem or to build optimal portfolios in the high dimensional case, we need to rely on the so-called like basic ideas of the random matrix theory. So the random matrix theory is a pretty old or relatively old theory and was or is due to Wishart and Wigner. They are the so-called the fathers of the finite dimensional and asymptotic random matrix theory. The basic idea of their random matrix theory is their empirical spectral distribution, or ESD. And ESD is nothing else as their empirical distribution function of their eigenvalues. So if we look at this formula here, it is simply the indicator function that our eigenvalues, the i's eigenvalue, is smaller than the pre-specified value of x. So very similar to the empirical distribution function, but just applied to the eigenvalues of our arbitrary matrix. So it can be shown that if our sigma n, the true covariance matrix, is the identity one, then this difference over here converges to their converges in the distribution to the square root of w. The w's have IID normal distributions on their on the main diagonal, and non-diagonal elements are 0, 1. There are some additional results like the Wigner's semicircular law and so on and so forth, but that's not that important here. What is important is the Stieltjes transformation, because it is, you probably will not see much of that on the slides later on, but it is extremely important for the proofs. So the Stieltjes transformation of the function with bounded variation g is defined in the following way. So mg is integral 1 lambda minus z, and then here we have our function of bounded variation, and we do it for every single value, complex value of the variable z. Now, if we compute this Stieltjes transform for our empirical spectral density Fn, on the previous slide for the eigenvalues, then we can show that the Stieltjes transform of this function Fn is or can be computed in the following way. So it is trace of our sample covariance matrix minus z times the identity matrix, the target covariance matrix, to the power minus 1. And this quantity appears very, very frequently later on in all the proofs. So this is a Stieltjes transform of our empirical spectral density of the matrix Sn. Now we are interested in the asymptotic theory, and this asymptotic theory is provided by the Silverstein theorem. He tells us that Fn, this empirical spectral density, converges almost surely to the function Ft. And this Ft satisfies, or the Stieltjes transform of this function f satisfies the following integral equation. So we have f over here in the Stieltjes transformation, and we have f over here in this Stieltjes transformation. And this function m, or the f, is unique for all z are in the positive part of the complex space. So in fact, we can get the Stieltjes transform from this integral equation for the asymptotic distribution of our empirical spectral density. Now, we don't go deeper into the theory over here, but I would just go now to the consequences and to our shrinkage estimate. So we know many parameters in statistics. We know the mean vector, we know the covariance matrix, and there are also a lot of theory how to improve the estimators for those parameters. For example, if we talk about their mean vector, then James Stein suggested, like 60 years ago, the James Stein shrinkage estimator, and this is the estimator that minimizes their quadratic loss. And we've seen that for higher dimensions, higher than 2 or 3, it is reasonable to shrink our sample mean towards 0 with some multiplicative constant. So this idea was extended many times and analyzed very carefully. The covariance matrix was also can also be estimated using the shrinkage technique, and probably the most popular contribution in that field are of Ledoux and Wolf. Ledoux and Wolf, in their very prominent paper in 2004, they suggested a shrinkage estimator of the covariance matrix. So there is a covariance matrix, the target covariance matrix, and they try to weight it. Now, if we talk about asset allocation and about portfolio weights, then it is very natural to shrink the portfolio weights directly. So we don't want to shrink the mean, we don't want to shrink the covariance matrix, like the key parameters. We want to shrink the portfolio weights directly. So I had a paper like many years ago where we just developed this idea from a more applied point of view in a lower dimensional case. Then there is a very prominent paper also of Khan and Joe, and he also gave a lot of comments on the paper I'm presenting here. And there are also other papers going into that direction, that we try to shrink not the parameters of the return distribution, but the portfolio weights. Now let's just try to introduce the very general idea of the shrinkage estimator. Assume that we have some high dimensional object H. We can estimate it using some historical data. The estimate is denoted by H hat. And our generalized linear shrinkage estimator is simply a linear combination of this estimator H hat and some target object T. So A, B are the weights. They can sum up to 1, but not necessarily. As for example, in their paper of Ledoux and Wolf, they do not sum up to 1. So we sum up the sample estimator and the target quantity to get something what is called a generalized linear shrinkage estimator. The weights alpha and beta are of course unknown, and they are typically estimated by minimizing some appropriate loss function. Can be some Frobenius norm for their matrices, and can be a Euclidean norm for their vector quantities, and so on and so forth. Now, if we talk about their covariance matrices, then Ledoux and Wolf suggested the following loss function. So it is expected Frobenius norm between the sample estimator of the covariance matrix and its counterpart. So n down here indicates that we try to estimate our sigma n using n observations. And they have determined the optimal weights, these alpha, beta, and delta over here. And they shrink the sample covariance matrix towards their multiplicity of the identity matrix. So they assume that the target has all the same variances on the main diagonal and has 0 correlations. So in fact, they shrink it to their identity matrix in some sense. Now, what we do here, we try to copy their idea of the shrinkage estimator to the portfolio weights. So what we do, let Sn plus be the generalized inverse of their sample covariance matrix. And our key idea is in the equation 4 here, that our generalized shrinkage estimator for the portfolio weights is a linear combination of the sample portfolio weights I have defined a couple of slides before, like the traditional estimator, and the target portfolio B. So the sum of all B's must be equal to 1, and we assume that this target portfolio has a bounded variation in some sense. So what we have over here is the same shrinkage idea of James Stein, Ledoux and Wolf, and others, but applied directly to the portfolio weights. Typical question is, what is B? B is something what is non-stochastic, and we believe must have good properties in their empirical applications. For example, everyone knows that equally weighted portfolio seems to have to show a good performance. So for example, we can take all elements of B equal to 1 over P. So it would be an equally weighted portfolio. Now, the S, relying on the formulas before, is given by the following quantity here, and we replace our sample covariance matrix by this Sn plus. So why do we need something else here? That's because we assume that our C can be larger than 1. So our ratio between the dimension and the sample size converges to some constant C. If C is smaller than 1, then everything is fine. We can compute the classical inverse covariance matrix. However, if C is larger than 1, then their inverse, this sample covariance matrix is singular, and we rely here on some generalization. It can be Moore Penrose, it can be any type of their generalized inverse metrics over here. So Sn plus is, for example, for simplicity, the more Penrose generalized inverse of the sample covariance matrix. So B is known, for example, their equally weighted portfolio, and what we are interested in is their parameter alpha n. So in the classical shrinkage estimation, typically you rely on some kind of loss functions like Frobenius norm and so on and so forth. Here, since we have an economic application, we believe that the loss function for the determining of the shrinkage intensity alpha n should be also economically motivated. So what we do, we take the same quadratic utility function we have taken before, but potentially with other parameter beta over there. So we determine our shrinkage intensity by maximizing, again, the quadratic utility function of our asset allocation. Those weights here, alpha n, they are the shrinkage intensity alpha n is stored over here, and over there, and we maximize it with respect to alpha n. Again, it is a quadratic function, and we end up with the following optimal shrinkage intensity alpha n star that depends on their sample covariance matrices, on their sample portfolio weights, on the target weight, and on the parameters sigma n and mu over here. Now, B can be set equal to gamma, then we have the same mean variance objective as before. It can be also set to infinity, then we'll have the global minimum variance portfolio. So we maximize the global risk of that. Now, if P is fixed, then our shrinkage intensity converges to 1. It's natural. If P is fixed, n goes to infinity, we estimate all the parameters here like mu and sigma consistently. They converge to their true counterparts. And if we have perfect information, if we have huge sample size, then we believe in our Markowitz mean variance portfolio. If P increases, then we still have some uncertainty, and all this theory, all these converges here does not imply. So this works only in their simple asymptotics. In a high dimensional asymptotics, it's not fulfilled anymore. Now, to show what happened there, it's very technical slide, but I just wanted to show you where this random matrix theory comes in. So if you look at the formulas over here, we see that everything depends on some linear forms or quadratic forms in the inverse covariance matrix. And this implies that we need some kinds of asymptotics or some consistency for the linear and quadratic forms in the inverse covariance matrix and its square. And this relies on the result of Rubio and Mestret 2011. They show that this quantity here converges in almost surely to some mz times the trace of the matrix theta p. Vn is something like our covariance matrix up there. We subtract the target and take the inverse one. And now this is very similar to our to what we had on the 3 slides on the random matrix series. So it is some trace, and then we have something over here. So it is very similar to this Stieltjes transform of their empirical spectral density. Now this result here is used to show all those convergences here, and those convergences here, they are of key importance for their portfolio weights. So imagine we have some identity vector here, and the inverse covariance matrix over there. That's exactly what we have, for example, down here. And if you multiply this y over here, then we have one vector, inverse covariance matrix, another vector. So again, we have then something like over here. So all those quantities are needed to analyze the asymptotics of those weights there. So relying on this stuff here, we can find their optimal shrinkage intensity and its limit. So this alpha n star that we had on the previous slide converges almost surely to alpha star. And this takes two different values, one for C smaller than 1 and one for C larger than 1. So we see that our optimal shrinkage intensity does not converge to 1, as one would have in the simple asymptotics, but it converges to some quantity, large formula that depends on all possible characteristics of the target portfolio B, like return of the target portfolio, variance of the target portfolio, and then return and variance of the global mean variance portfolio. Important here is this S. This is our curvature of the, or the slope of the efficient frontier. Now, let's have a look how this alpha star looks like. So these two pictures here, they show our alpha star, shall be alpha star up there, at the function of C. So if C is very small, it means that our sample size is very, very large compared to the dimension, that our alpha goes to 1, and we believe in our true Markowitz portfolio. So we invest a lot in our Markowitz portfolio. If our C goes to 1, then we realize that our covariance matrix, sample covariance matrix, becomes almost singular. This renders a lot of uncertainty in our portfolio, and our shrinkage intensity converges to 0 or tends to 0. It means in that case, we'll invest completely into the target portfolio. And then if C increases again, we see that our Moore-Penrose inverse covariance matrix would stabilize in some sense the wall estimation, and we'll invest more again into their traditional mean variance portfolio. So on the left-hand side, it is for the case when beta is equal to gamma. And on the right-hand side is if beta is equal to infinity. Those are the two different calibration criteria we have defined on the previous slides. So this is very natural, the results here. Different lines here, they actually show the condition index of our true covariance matrix. It's like the ratio of the largest and the smallest eigenvalue. If ratio is very large, it means we have more or less unstable metrics, or ill-conditioned metrics. If it is small, then we have a well-conditioned metrics. So let's go further. We are interested not only in the weights, but also in the losses. And here we compute the relative loss of the true portfolio and our generalized shrinkage intensity portfolio. So it is the utility of the true portfolio minus the utility of the portfolio we have estimated with our shrinkage, divided on the utility of the true portfolio. And it can be shown that this quantity here, it is some strange combination of the losses of the traditional estimator, mean variance portfolio, and loss of the target portfolio, plus something. Again, we have to distinguish between C smaller than 1 and C larger than 1. And then this LS here can be computed explicitly using those two large formulas over here. But in fact, we can plug in those two things instead of LS up there, and we'll get our loss. So now let's have a look how this loss looks like. In the upper part, we see the relative loss as a function of C, and in the lower part, we see the relative loss as the function of P, of the dimension. So again, we see that our traditional estimator, simple maximum likelihood estimator of the parameters, it really explodes over here. So if C comes to 1, our covariance matrix becomes extremely unstable, and our portfolio is in fact useless. Its loss is like infinity compared to the true loss of the portfolio. The target portfolio has always the same loss, so it is constant. It doesn't depend on C, in fact. And our Oracle shrinkage loss, it is better than the traditional one and then the target if C is smaller than 1. We have some stability problems around 0, and then it remains good also if C increases even further. So on the left-hand side, it is for beta equal to gamma, and on the right-hand side is for beta going to infinity. If we have a look at the relative loss as a function of P, we see that the relative loss of their Oracle shrinkage intensity is always the best one, regardless of the dimension, and the difference is very, very substantial. So on the left-hand side is again for one beta and for another beta, as in their upper two pictures. Now, the problem with all this stuff is that our shrinkage intensity, this alpha star over here, it depends on the unknown parameters. So it depends on mu and sigma. Those are unknown and they have to be estimated. And that's exactly what we tackle over here. So we offer some kind of bona fide estimator by computing consistent estimators of the parameters over here. So for example, if we need to plug in to estimate VGMV, we pick up the consistent estimator in the high dimensional asymptotic for this quantity. So we take, for example, this one. If we need to estimate the slope S of our efficient frontier, we pick up a consistent estimator for C smaller than 1 or C larger than 1. So we don't simply take a set as one would do, but we pick up a high dimensional consistent estimator of those parameters over here and plug into the formula before. So at the end, we get something like this. Here, everything is already estimated, and we still get a consistent estimator of our optimal shrinkage intensity alpha star. So in fact, here everything is known, and we can really plug in their parameters and compute the corresponding shrinkage intensity. So let me show you some results. I have just perfect timing, more or less, the results from the empirical study. So we applied this approach to almost 400 constituents from Standard & Poor 500. The data set covers like 18 years of daily data. We pick up this strange number of the constituents because we picked up those assets that were traded in Standard & Poor for the whole period of time. So it is less than 500 at the end. Now, typical critique point from all the reviewers is that you pick up one single portfolio and try to show us that it works well. To avoid these kind of comments, we robustify our analysis by picking up 1,000 different random portfolios, and we average our results for this 1,000 random portfolios. So we don't consider a single portfolio, we draw from those 400 constituents 1,000 different portfolios of the corresponding dimension. So it is really very robust. Now then, we would like to robustify our analysis with respect to the target portfolio. So once we take equally weighted portfolio, so B is equal 1 over P, what we have discussed before. Then we take equally correlated target. This is a very interesting portfolio because what is difficult to estimate are the correlations in the covariance matrix, or the covariances in the covariance matrix. And what we say, well, since all the correlations are anyway very small, let us simply average all the correlations, pick up the single value and plug it into the estimated covariance matrix on every single non-diagonal element. So we believe that all the correlations are the same and are equal to the average correlation for the whole matrix. So we stabilize the estimation of their covariance matrix. And the third target we consider is their Fama-French target. So you recall this high minus low, big minus small, and so on and so forth targets, and we use this factor model to estimate the covariance matrix of the returns. So it is based not on the historical data in some sense, in the classical way, but on their factor model, three-factor model of Fama and French. So we have three targets. Then we also need some kind of benchmarks to compare our model with. And the first one is the traditional estimator, ML estimator with Moore Penrose. Then we have the shrinkage portfolio of Canchou, and we have the nonlinear shrinkage of Ledoux and Wolf for their covariance matrix. So this is not the shrinkage I have shown before. This is a new one, and it is a kind of a nonlinear shrinkage estimator for the covariance matrix. Now, the problem is that if our C is close to 1, then everything becomes unstable. Regardless what you take, if you take traditional, if you take some Moore Penrose, everything becomes extremely unstable due to their like almost non-invertibility of the covariance matrix. To overcome that problem, we rely on the Tikhonov or on the rich regularization of the precision matrix. So we try to estimate our precision matrix, inverse covariance matrix, in a like shrunk way. So we add something like delta I over here and delta I over there, and in the middle we have our sample covariance, the sample covariance matrix. So at the end we get we push our sample covariance matrix away from a singularity. Delta is selected to be 1 over P, but the choice of delta is in fact irrelevant here. So this is just a small extract from the empirical results we have had in our paper. So just to give you some feeling what is in this large table, the first block up there, it contains the results for C equals 0.8, like 400 dimension and 500 sample size. And here is C is equal to 2.0. So our dimension is twice as large as their as a sample size. Now, in the vertical, in the columns here, we have a certainty equivalent, that was the value of the utility function. We have Sharpe ratio, we have value at risk for alpha 0.05 and 0.01, and we have the expected shortfall again for 0.05 and 0.01. Now in the rows, like in the blocks over here, we have the targets. So we have equally weighted target, we have equal correlation target, and we have Fama French target. And in the rows, we have the corresponding strategies. So this is a classical one, traditional with reach, Ledoux and Wolf. And then we have our bona fide with reach, target, and Kanjo. So we have really very, very robust result. And again, all those numbers over here, they are based on 1,000 random portfolios of size 300. So it is very robust in some sense. And the trading period consists of 1,000 days preceding the last day of our sample. We see that like the best strategies are highlighted in bold here. If C is 0.8, for example, then our bona fide reach estimator is the best one if we took a look at the certainty equivalent, if you look at the valued risk, and if you look at the expected shortfall. If you look at the Sharpe ratio, then the Kanjo target is the best one. Kanjo approach is the best one, but it is natural because it aims to maximize their Sharpe ratio. So it is built, the Kanjo portfolio is built to maximize the Sharpe ratio of their portfolio in some relative sense. If we increase our C to 2, then we see that our bona fide or bona fide rich estimator dominate all other alternatives, either it is traditional or Ledoux and Wolf or target, or their a Kanjo cannot be applied here because it is developed only for the case C smaller than 1. So their suggested shrinkage estimator dominates really all the benchmarks and classical estimator with respect to all those performance measures out there in a very robust way. The same results apply also if we take a smaller sample like 100 assets, or if we take beta equal to infinity, like different criteria we have discussed so far. To show you the last slide, to show you the dynamics of our shrinkage intensities, like this picture showed the dynamics of the shrinkage intensities. We see on the horizontal axis our time span from 2000 to 2018, and different lines here show the shrinkage intensity for different values of C. So if C is small, 0.2, then alpha is very close to 1, so we rely a lot on our traditional portfolios with maximum likelihood estimators, and if we increase our C to 0.8, this green one, then our target portfolio becomes more weighted. So we put more weight on the target portfolio. And if we go beyond 1, then again, our traditional estimator with move pen rows or with reach become a little bit better. And all those spikes here, they also I can tell you a huge story about the economic background on those spikes here, like 2007, 2008 crisis and so on and so forth. But everyone can think of their motivation behind that on his or her own. So this is the list of the references, and thank you so much. The paper is on the archive if you're interested in the details or in the proofs.